and I will find the lecture, which is Parallel IO 3. So we're not going to talk about particularly how MPI-IO interacts with Lustre, but we're going to talk about how MPI-IO works. So this is, in places, maybe a bit too detailed, but the point about this is it's basically trying to give you an understanding, and this is particularly for MPI-IO, but hopefully true for almost all IO libraries, how they work, and to give you some idea of what the issues are going to be. So what I'm going to talk about now, I'll try and share the window, is I'll talk about how you do MPI-IO and how it works. Okay? And then what we'll do after that is we'll look at some MPI-IO benchmarks. So this lecture is going to cover the MPI-IO model, what the basic file handling routines are, setting the file view and achieving performance. Now, I'm going to go through MPI-IO in some detail because it's the one I understand the most. I only have very brief descriptions for HDF5, NetCDF, and ARCHER2 in a later lecture, but conceptually they'll be the same level of things. It's just the details will be different, but you know, the conceptually that they're doing the same thing. So, concerning MPI-IO controller. Controller IO uses a single process for read and write. This requires a buffer to hold the entire thing control, and it's not scalable to many processes due to memory limits. Okay. ARCHER2 has thousands of nodes, each with hundreds of gigabytes. So that's basically, many terabytes of data, terabytes of memory. But if you do controller IO, you're saying I've got terabytes of memory, but my cannot have a data set bigger than 2 gigabytes because that's the maximum that can fit on a single process. It's clearly not sustainable to funnel all your IO through a single process. And we've seen that if you do that, you will be getting an IO speed of about 700 megabytes per second. So even for a single node, 700 megabytes per second, say for 100 gigabytes, is minutes. Okay, minutes. So you're going to take minutes per node, and if you have hundreds of nodes, it's hundreds of minutes. So literally, you're just not. That's not sustainable. So the MPI-IO model is each process describes what subsections of the file it owns. This is done using standard MPI data types. That's not particularly important. You then pass these into the MPI routines in this critical phase I said, where you tell the MPI library which parts of the global data each process owns. Then the data is automatically read and transferred directly to sorry, this is talking about read. So I think for historical reasons, this lecture focuses on read. If you're doing a programming exercise for MPI-IO, I would get used to write an exercise which reads a file, because it's easier then to check the file is correct, because you can see if you've got the right data. Of course, my bench IO writes. So thinking about a write, the data is often transferred, is read from memory and transferred directly to the file. But this text here, data is automatically read and transferred directly to local memory, is true for read. Read and write are really, when you see file read or file write, you just switch them around. There's no single large buffer, no explicit controller process. So MPI-IO model is a collective process. If you think about write, everyone tells the IO library which subsection of the global data they own. You tell everybody to write, and the IO library sorts everything out and creates the file, a single file on disk. But I said these slides will, as I said, these slides use reading. So there's 4 stages: open the file, set the file view, read or write data, or close the file. And in fact, open a file, read or write data, and close the file is what you would do for any IO system. Even Fortran, C, Python. All the complexity of parallelism is hidden in setting the file view. So I said write is probably more important in practice than read. Most HPC programs write, I don't know, an order of magnitude data more than they read, but these slides use read as an example for historical reasons. The exercise I used to use for this lecture was developing a read. I gave you a file to read from disk, and you could check you got the right answer, but just replace read with write in all the calls. So to open a file, it's MPI file open. It's collective across a you give a collective across a communicator. This defines which subset of processes you're going to use. Often it's MPI call world. It's everybody. You give a file name, an access mode, and some info parameters, and you get back a file handle. This is just like a FP equals file open, and you get back a file pointer. It's completely analogous. It attaches the files to the file handle, and then all future IO calls you pass this file handle. And this is analogous to C file pointer for a Fortran unit number. The root is collective across the communicator. It has to be called by all the processes in that communicator. And the access mode is the standard thing you do: create, read only, write only, read, write, whatever the standard things you do. But there's nothing special about this. There's nothing particularly interesting or special about this call, other than it's done in parallel across all processes on the communicator. And if you're familiar with MPI, you normally think that all MPI routines take a communicator as an argument. MPI file routines don't take a communicator; they take a file handle. But the file handle knows which communicator it is attached to. So a typical one in C, MPI file handle, access mode is MPI mode read only for a read example, MPI file open, com world, data.in, the access mode is read only. I'm not going to pass, you can pass hints here, but I'm going to talk about that later. We just pass, so there is this info object which allows you to pass system specific hints, but we'll come back to that. And you get back a file handle. If you want to write files, you have to create them as well as write them. So you have to OR the access modes together: MPI mode create or MPI mode read only. Closing a file, MPI file close. It's collected across the communicator. Yeah, big deal. Reading data. So MPI file read all or BenchI use MPI file write all. It looks so. The way to think about MPI-IO is a read is like a receive from a file, and a write is like a send to a file. Okay? So MPI file read all reads a buff into a local buffer, which is of count data type, and you get back a status, and you're reading from a file handle. This looks just like an MPI receive. You're receiving data from the file into the buffer. This looks just like an MPI receive. And in fact, the MPI write is just like an MPI write is just like a send. So MPI read is like you're receiving data from the file. MPI write is like you're sending data to the file. So that is quite a good analogy. So this read would read count objects of type data type from the file on each process. It's collective across the communicator associated with the file handle, and it's like a CF read or Fortran read. But if you think about it, this looks a bit weird because we've opened the file. Okay, now we've done a read. So MPI file read all is a collective routine, says everybody read. But nowhere here am I telling the IO library that different processes should read different data. So there are no offsets in the file. You've not specified start at this location. Okay, so why don't all the files receive the same data? Why don't all the processes read or write the same data? Why do all processes read, or why do all processes? How do processes know where to read the data from or know where to write the data to? That is in this intermediate stage, and an MPI calls that setting the file view. In MPI, setting the file view is telling the IO library, the MPI library, which subsections of the file your process is interested in. So the actual positions of the read depends, or the write depends on the process file view. And this is something which called, so MPI set file view is, again, if you're not familiar with MPI data types, maybe you're not too familiar, but the concepts are hopefully quite understandable. This is the crucial stage, and different IO libraries have their own way of doing this. MPI calls it setting the file view. You specify a file handle. This is the file you're interested in. You specify displacement, which is how far you want to. Each process can say, I don't want to read from 0, I want to read from a megabyte in, 2 megabytes in. You specify an E type. This is what the file is made of. So if your file is integers, this would be MPI integer. And you specify a file type. And the file type is this data type which tells MPI which subsection or subsections of the file that you're interested in. You pass another string and then an info object. It's all quite a lot of stuff here. But the displacement specifies the starting point of the file in bytes. The E type is the elementary data type, which is the building block of the file, which might be doubles or whatever. The file type is the important thing. That specifies which subsections of the global file each process accesses. The data rep is to do with the format of the file, and info is the system-specific information. So the way that you do file views is you can specify these using MPI vectors of subarray data types. But the important point is that if we look at this exercise here, the global file, remember our canonical example, a 4x4 array across a 2x2 grid of processes. In this example, rank 1, which is this blue process here, has a little array of 4 elements, size 4. However, they are not a contiguous section of the file. They are elements 3, 4, 7, and 8. So it's that one and that one. The MPI file set view, your data type, you have to pass a data type which is a 2x2, the 2x2 section of a 4x4 array. You can define data types in MPI which say, look, this data type represents the 2x2 subsection of a 4x4 array in the top left-hand corner, and they're called MPI subarrays. If you can do that, what you do is you pass that to the MPI library. So the file type for the blue process is this thing. It says, I want to look at 3, 4, and 7, and 8. And the important point is, once you've set the file view, that's like a mask. So the file view says, I am only interested in these portions of the file. So if rank 1 specifies this template here, which we can define as a vector or an MPI subarray, if you're familiar with those, once we've done that, rank 1 just sees 3, 4, 7, and 8. So if rank 1 says read 4 elements, it reads 3, 4, 7, and 8. If rank 1 says write 4 elements, it writes 4 elements, 3, 4, 7, 8, and skips over all the gaps. So the file view it masks that everything you're not interested in and says, I am only interested in this section of the file. Once you've done that, you can just do linear reads and writes. You just say, I want to read 4 elements, but you read elements 3, 4, 7, and 8 because MPI knows to skip this thing in the middle. So the file view is a mask which says, I am only interested in this element of the file. And other, as I said, a lot of libraries have their own way of doing this, but MPI does it with these things called file views. The file type should tile the file. So if you want the entire file to be read in, it's important that the file types for the yellow, blue, green, and red process match up. So if you were doing this simple example, it's important that rank 0 has this, this, this. If we add them all up, each process has its own view of the file, these elements, these elements, these elements, these elements, but together they add up and stride and cover the entire file. So if we set that up correctly, each process only sees its particular part of the file, and then can then do linear reads or write. I just want to write 4 elements or read 4 elements, and they will go to the correct place because you've masked out everything else. And that's the way that MPI-IO works. So there are some other parameters there. There's something called the data rep, is a string native internal or external 32. External 32 is a portable format. I would always use native. This just dumps the raw bytes to memory. I/O is slow, okay? Every time you do I/O, your program is stalled effectively, normally stalled. That's for read or write. You just want to get the data out as quick as possible. So I always just do a native format. Just tell MPI, just dump the data onto disk as quick as you can. Don't do any conversion. There are various slightly more portable formats. Internal is probably portable between the same MPI library on different platforms, but not globally portable. External 32 is readable by MPI on any platform, but there will be some conversion here to this format, which will take time. So I would always recommend native. This is a kind of a technical point, which I meant to hide these slides. Apologies. If you're going to use MPI-IO, I would recommend setting the view with. I would recommend setting the view with subarray types. You can do the I/O using vector types, but that has its issues. So apologies, I meant to hide these slides because they're a bit too detailed for this version of the talk. So in bench I/O, if you run the MPI-IO in BenchI using MPI-IO, it uses MPI subarray types for the file type. And these are basically defined by 3 integer arrays. And the reason I mention them is that these are the clear things you need to specify. And there will be equivalents in the other IO libraries, which I will flag up. But in MPI-IO speak, the 3 things you want are the sizes, the global size of the entire array, and that is, for this trivial example, 4 by 4. So let's think with the blue process. What do I have to do? What's my file type? Well, I have to specify the size of the enclosing array, which is 4 by 4. The subsize is the size of my array, which is 2 by 2, but I also have to say where it starts, where this subarray is located in the global array. So sizes, subsizes, and starts are the important parameters to define this MPI data type, to say which part of the global file am I interested in. Okay, so I'll come back to that. So here, the blue rank 1 says the global sizes are 4 by 4, the sub sizes are 2 by 2, and I start at position 0, 0, 2. That's my bottom left-hand corner is. So Sarah asked if the rank size. Do you mean if the size of the? Do you mean if the size of the array is different on each process? Is that what you mean? Yeah. Okay. So that would be quite. So basically, imagine that it was a 3 by 3 array. Okay. So that the blue rank would then say the global size. Everyone agree on the global size being 3 by 3, but the blue rank would say my local size is 2 by 1, and I start at 0, 2. The red processor would say the global size is 3 by 3. My local size is 1 by 1, and I start at position 2, 2. So each process specifies the parameters appropriate to its to what it has. So that's how you can do it. You can cope with different sizes. Is that clear? Each process specifies a different. So the file types can be different on each process as long as they match up, as long as they tile together. Does that answer your question? So I've deliberately got a very, very simple example here. But you're right. It does. Is that okay? Yeah, fine. Yeah. So what we did here is we used all. Okay. So if you imagine, let's have a look. I did MPI file. Sorry. Read all. Let's imagine a write example. Let's say MPI file write all. Okay. Well, imagine we didn't do write all. Okay. Imagine we just did MPI file write. Okay. So we said, so MPI file write all is a collective routine. It's guaranteed everyone calls it. Okay. Let's imagine we didn't do MPI file write, or we did MPI file write, which is an individual routine. The IO library will get a request from the blue process to write this data to these portions in the file. Okay. Because if you call a non-collect, and this generalizes to other libraries, which is why the idea of collective I/O is very important. If you do individual I/O, i.e., non-collective I/O, if you issue an I/O request from the blue process, the IO library has no idea if or what other processes are doing, if other processes are doing I/O, and if so, what they do. So the only thing it can do is it basically has to lock the file. Say, I don't know what other people are doing, so lock the file, do its writes, flush them to disk, and then close the file. It has to serialize the I/O. If you do individual I/O, where each process just specifies its I/O request individually, it will work. Because the IO library has no idea what other processes are doing, then it basically has to serialize the IO, process each IO request one by one, and you get very slow performance. One of the exercises in BenchI/O is to replace MPI file write all with MPI file write and do non-collective IO. It's so slow that you probably can't run it on more than one node. It'll take, you get cripplingly slow IO performance. What the IO library can do, that if you do MPI file write all, it can say, everyone's writing. So I know the blue process is doing this data, but I also know the yellow process. I could merge those together and do one big write. So the critical aspect of parallel I/O to get the right answer is this, in MPI speak, setting the view. Every process has to tell the library which data it owns. But the absolutely critical aspect to get performance is to do collective I/O. That allows the library to basically, it knows every process is doing I/O at the same time. It knows what I/O the processes are doing. It can then merge things together and do lots of clever things. So for example, here, it could, if you do a write all, it could say, okay, I know that ranks 0 and 1 are writing, so I can collect the data into it and do a one really big write. And the same with ranks 2 and 3 to do one really big write. So the apps and all other I/O libraries, things like Adios, HDF5, NetCDF, also have collective and probably have collective and non-collective options for I/O. It is absolutely essential that you do collective I/O. And again, the exercise is to try non-collective I/O for bench I/O, but it's so slow that it's quite painful. The info objects here, the info objects allow you to pass hints to MPI-IO. For example, you can specify things like stripings and such like. However, I find it more convenient to not specify anything like that from, if you want to control things like the striping and the stripe size, you have two options. One is tell MPI-IO what to do, or the other is to specify it on the command line with Lustre command. I definitely prefer the latter. So when I do I/O with MPI-IO, I write programs which just have info equals MPI-IO info null. I give no hints at all to the MPI library. I control all that externally with my Lustre file commands. So for example, I would, on ARCHER2, it's much easier to tune the Lustre file system than to use MPI-IO hints. So I like to write a completely vanilla, generic, portable MPI program which has no hints or assumptions about things, and it's much easier to do experiments that way. You can rerun the same program by changing the settings on the command line. So the summary is MPI-IO calls are deceptively simple. The user's got to define appropriate file types to the file viewers correct on each process. This is the difficult part. Having done that, though, you must use collective calls when you can. It enables our library to merge reads and writes. It allows it to do a small number of larger I/O operations from or to disk. Other libraries, and it doesn't have to do any locking as well, because it knows what everyone is doing. Other I/O libraries sit on top of MPI-IO. You may have used HDF5. That's why I go into MPI-IO in some detail. So I can see that some people have actually run the exercise, but let's just trying to find the the MPI performance is to do this. So for parallel I/O, okay, we're writing a single file, but hopefully we can write it to multiple disks. So we would hope that the bandwidth scales with the number of stripes. The number of stripes, the number of disks we're using, we would hope that the bandwidth would scale with the number of stripes. So what this is doing is saying, I want each process to have 128 by 128 by 128 array, and I want to do MPI-IO. I haven't specified the striping here, so if you look at the documentation, that means it writes to all the files. So this will do MPI-IO of a 128 by 128 by 128 array locally on each process to file. And the idea here is to try 2, 4, and 8 nodes and compare how it looks. Okay, so these are these are extra things, but this is really the key example. So I will just show you to see if we get the. I'll share. Let's take a note of what it should be. So I won't run this, and you can go on and do the other numbers of nodes. I'll just do the initial one on one node. So I'm struggling with sharing the right window, which is this guy here. So if I edit the file, I wanted to do one node. fill it up. I wanted to, I just cut and paste this. Let's see what we get. So I'm not running. If I list the strip start, you can see it's writing to the unstriped. Let's do ls minus lh. It's written, oh, now it's gone to the full stripe. Okay, but you can see if you do an ls while you're running, it's finished now. You can see the file appearing. So I caught the MPI-IO.that file being written to the unstriped, and I missed the stripe, and now it's on the full stripe. So I deliberately, the benchmark deletes, as I said, deletes the files at the end deliberately, so we don't end up running out of disk space. And what do we get there? So 108 processes running on one node. It prints out the node number. The process grid is 4 by 4 by 8. Remember, I asked for 128 processes. It arranges them in a grid. The local array size is 128 by 128, but that goes up to 512 by 512 by 1024. So that turns out to be 2 gigabytes of data, if you think about it. I'm using MPI-IO, and I'm writing to these. And you'll see that I get rather disappointing I/O rates. I get, if I write to the unstriped file, I get basically what I got for serial I/O, 700 megabytes a second, and it increases slightly with stripe count, but not brilliantly. And the reason is, well, we can come back to the reason, but it was useful to get the data. So to get good parallel I/O, you don't just need to use all the OSTs, which we're doing here by using a striped file. You also need to have lots of nodes writing. Remember, each node is a client of the file system. The problem here is we have a file striped across lots of OSTs, across lots of disks, but we're only running a single node. So that is effectively only one I/O client. And so we don't get very good bandwidth. The only way to get good bandwidth is to have lots of people writing, which is lots of nodes, lots of I/O clients, and also lots of people being written to, which is lots of OSTs and lots of disks. So you would hope to be able to, that this should increase if you run on 1, 2, 4, 8 and more. Now, Maureen said that she didn't get such I/O. So why don't we take a break to let people run this and then come back just before the break, before lunch, and we can maybe discuss the results. That would be useful. So let's, but please if there are any questions, but let's, so that's the way I'm going to do it. We'll do a practical until 12:50. You can play around. Then we have a wrap up at 12 to 1. We maybe look at the results. And then the next lecture will be at 2 o'clock. Slides are recorded to the virtual tool containing details of the result are available from the Archer course repository. If we click on there, we then get the slides. Can we see that? Yeah. And there is a diagram in here which illustrates it there. That's what it does. Yeah. So it's just a generalization. But if I had an array on 8 processes, it might be a 2 by 2 by 2 grid, and that would be the. Does that make sense? That's so yeah. So what's the yes. So the process of it, yeah. So it's like each of these is a block of 2 integers. Yeah. So so there's 8 elements. So just to simplify things, But the point about this is just to show that even for an almost trivial problem, an 8 by 8 by 8 array. Sorry, a 4 by 4 by 4 array on 8 processes, completely structured, almost as simple as you can imagine. The I/O pattern, the translation of the data on the processes to the file, is surprisingly complicated. This should be read across and across. You know, that goes along there and then along here. But you know, it is, you know, process 7 is writing to 4 different parts of the file separated by long pieces. That's really just to show that although a bench IO does a very simple, what seems like a very simple IO pattern, simple problem, the I/O pattern is complicated. Yes, sorry, I had misunderstood your question, Sarah. You're right. Maureen says the P's are not the data, but the process that writes the data. So I've run 4 jobs. The jobs and I've got some very poor repping. So this is 1 node, 2 node, 4 node, and 8 node, and this is 1, 2, and 12 stripes. Okay. Now you can see that the time goes up because we are running what you call weak scaling, in that the problem size per process is staying the same. So when we run on 8, if that's just for simplicity, I mean, you could do the other way around. You could fix it. It won't make any difference to these results. So that's the most important thing. First of all, is that if you don't stripe the file, yeah. So you're using MPI-IO, which is quite sophisticated. If you don't stripe the file, you get 0.6 gigabytes per second. You get the serial I/O rate, which we previously measured. However, if you do stripe the file, it does scale with the number of stripes, roughly. So with 1 stripe, you get 1.5, 1.15 gigabytes, 1.8, 3.2. So if that's pretty okay, you know, if you'd said that's not so good up to there. So I think that is that what you said, Maureen. Okay, much less it was okay. When more in the MPI test, yeah. So I think this is just I think this is but this is just some kind of contention. I mean, the scaling isn't perfect. There's always going to be an overhead. I don't think it is. I don't think it's because of the divisor. You still have more process. You still have more stripes than nodes here. You have 8 nodes and 12 stripes. They should all get their own stripe. It should be better than that. It could be. I'm kind of jumping ahead here, but it could be because of the actually a problem with the MPI library. So I'm jumping ahead here, but you'll see it as one of the later. This is a useful thing to do, actually. If you think about it, this data aggregation it has to do. I want to grab data from this guy, this guy, this guy, and bring it all together. It requires MPI collective calls, things like gathers. Now, the default MPI implementation, which is something called OFI, is not particularly brilliant. So there is an alternative. There is an alternative implementation of MPI at the very lowest level called UCX. Now, this version of MPI seems to have better collective behavior. Yeah, nothing to do with MPI-IO so much as the collectives. So the MPI-IO is having to do a big gather of data into contiguous chunks. That uses an MPI collective routine, possibly MPI gather internally. And so let's see if that helps. So all I've done is change the MPI library, and it's running now. We can see that it's producing not running yet. There's the MPI-IO that appearing unstriped, getting bigger to 2.3 gig. It's going to get to sort of, I think, 16 gig, maybe 6 gig, 9, 11. It's going to take, I think, 16 gig. It will top out. This is the slow one. That's finished. Now we should do the other one to be a bit quicker. There is an overhead to deleting the files and stuff. So there it is in striped. It's bigger. It's going a lot faster. And then we're getting, yeah, that was much quicker. It's 12 gigabytes now. So that's presumably run. So let's have a look at if how that worked. What did we get? That, okay, so that's a lot better. Isn't that better? What did we get before? Yeah, so actually you can see here. So actually, I think what has actually happened is it's an MPI problem. That the MPI collectives have stopped scaling from there to there. You should run all these with UCX, but actually you'll see you get a lot better here. That's why. So actually this is a slight problem with MPI. So it's MPI having issues rather than MPI-IO. It's unfortunate, yeah. So that is interesting. The reason we don't recommend UCX as the default is that it's not the most supported version, but it's faster for collectives, but it's slightly slower for point-to-point, and it's a global change in your whole program. So it's horses for courses if it speed up, but for MPI-IO, it really helps. In fact, it might be worth I don't know if you could be bothered more if you could rerun all of. Do you see at the end of the sheet where I give those magic commands? If you could maybe rerun all 4 again, that would be very useful. I don't have the data to hand, but that would be interesting. So I think it will scale a lot better. So you're right, that's an interesting observation, but it's an MPI problem, not an MPI, not a file system problem, and it's unfortunate. But yeah. Okay. Okay, so that was useful. It seems to be getting some interesting results. We will come back. That's the program. We have lunch now. I need my lunch, I have to say. I'm just looking to check that So we're going to come back after lunch. We're going to do talk about configuring the Lustre file system, and then I'm going to talk about higher level parallel IO libraries. I just want to double check. I also have some tips, and I think these are in the just one second. Yeah. So I have a few copies. Yeah. So I'm going to talk about how to configure the Lustre file system, and that also touch on how MPI actually works internally in terms of how it decides how many nodes to write and how it does what's called data aggregation. Then we'll do a small practical, and the final talk will be about higher level parallel IO libraries, and we finish at 3:30. Well, I'm around till 4:30, but there's I'll finish the lecturing at 3:30, and then I'll be around until 4:30 to answer any questions.